So, to describe a concentrated load, we have a beam that has two supports, and we have two forces, or multiple forces I should say. And this is described as a concentrated load. This becomes important when we start looking at distributed loads. And we can see this in this problem here, where we have, just clean this part up, so in this problem we actually have two distributed loads, one at the top here and another one on the side. So we need to turn that distributed load into a concentrated force. So we need to go back this way. So how do we do that? If we take a look at that distributed load, what do we have in the first one? Up here, we have a beam and this distributed load occurring, and this is 3 kilonewtons per metre. So the units here is very important. So the units for my distributed load would be newtons of force divided by distance. So if this distance is given to us, and in the diagram it's 3 metres, to calculate what the concentrated force is going to be, it's going to be the area of a rectangle. So the area is going to equal the length times the breadth. The length is 3 metres and the height is 3 kilonewtons per metre. So what happens here? My metres cancel out and I'm left with a force. So my force is going to be 9 kilonewtons. And this is my concentrated force. So the question is, where does my concentrated force sit? It needs to sit exactly halfway between this beam. So at 1.5 metres. So my equivalent force is going to be 9 kilonewtons. And we can do exactly the same to this force. So here, what are we going to have? We'll have the side with a distributed force, and it's 2 kilonewtons per metre. My distance is 4 metres. So I want to calculate the area of that rectangle. So I'm going to have the area is going to equal 4 metres times 2 kilonewtons per metre. My metres will cancel out and I will be left with 8 kilonewtons. And where is this concentrated force here going to sit? It will sit halfway through the beam at 2 metres distance. So things get a little bit different when we start looking at triangles and looking at the distributed load of a triangle and converting that into a concentrated force. So let's take a look at a triangular concentrated force. See if this pops up for us. Here we go. So here we have a triangular distributed load, and here's my triangle, and I have a height of the distributed load, and I also have a width. So let's take a look at this problem. So if I draw my triangle on a beam, and the height of my triangle is 3,600 newtons per metre, and the length of my beam is 3 metres. So when I was looking at a rectangular distributed load, it was the area, so it was length times breadth. But now, with a triangle, we have the area of a triangle. So the area of a triangle is going to be half base times height. So we have half times the base, which is 3 metres, times by the height, which is 3,600 Newton on the metre. Again, what am I going to do? My metres will cancel out, and I'm going to be left with newtons, and that's going to give me 5,400 newtons. So this is my concentrated force. So on a triangular distribution, where is my concentrated force going to sit? So basically, it's at the centroid, and the centroid of the triangle is going to be somewhere around here, which is actually, it's a rule, it's 1/3 distance from the heavy side. So 1/3 times 3, so 1/3 times 3 is going to be 1 metre. So this distance here is 1 metre from the heavy side, is where our concentrated force is going to sit. So there's pretty much 2 things you need to remember when it comes to distributed load: a rectangular distributed load and a triangular distributed load. And whenever you have a distributed load, you always need to turn it back into a concentrated force.